Assalamualaikum warahmatullahi wabarakatuh. In the previous lecture, we have discussed about step by step how to draw the locus based on several rules. So this is the rule that we have discussed before. So in that lecture, I also give you an example to make sure you can understand how you can draw the locus. So now for today, let us look at another example. For example, we have a closed loop system, this one, with gs equal to s plus 4 divided by s times s plus 1 times s plus 2. And with k, this one we consider as a controller. So we call proportional control. And the system with feedback, unity feedback, enter at negative, so we call negative unity feedback. Before we can plot the roller curves, so we have to find the characteristic equation for this system. So based on this closed loop system, so we can find the characteristic equation by employ the formula 1 plus kgs times hs. After we employ that formula, so we get our characteristic is become like this: s times s plus 1 times s plus 2 plus k s plus 4 equal to 0. So we solve this, we get s cubed plus 3s square plus 2 plus ks plus 4k. This is the characteristic equation that represent this system. Based on this characteristic equation, so first we have to find the location of pole when k is equal to 0. So when k is equal to 0, so we just put 0 here, and then the pole is only located at 0, and this one s equal to 0. And from this one, s plus 1 equal to 0, s equal to negative 1, and another pole is s equal to negative 2. While for zeros, we just take this numerator. So this part, s plus 4 equal to 0. So s equal to negative 4. This is 0 for the system. So based on this, so we know that when k is equal to 0, there are three poles, which is 0, negative 1, and negative 2, and 1, 0, which is at negative 4. So when k is equal to infinity, so because we have 1 0 here, so that's mean one of the pole will go to that 0 and other pole will go to infinity. So after we identify pole and 0, so next we identify the number of branch. Based on the information about pole and zeros, so we can know the number of branch, where the number of branch is number of pole minus number of 0. So in this case, we have three poles, 1 0. So that's mean number of branch is only 2, because 3 minus 1. So that's mean equal to 2. So for rule number 3, so all root locus should be symmetry with the real axis. And next, we go to rule number 4, and where the rule number 4 is about we have to determine angle of asymptote and intersection of asymptote. For angle of asymptote, we just apply the same formula that we have discussed before, where the formula is 2k plus 1 times 180 degree divided by number of pole minus number of zeros. So in this case, we have 3 pole, we have 1 0, so we just put 3 minus 1 here. So that means this part become 2. So when we put k is equal to 0, so we get the value become 90 degree. So when we put k equal to 1, the value become 270. When we put k equal to 2, so the value become more than 360. So that means we just use these two angle. So because angle of asymptote must be less than 360. Okay, next for intersection of asymptote, we just use the formula where summation of pole minus summation of zero. Summation of pole means that we just add all this pole, and that means 0 plus minus 1 plus minus 2. So this one become negative 3. Okay, minus summation of zeros, we have only one zeros here, just put negative 4 here. So minus minus become positive, so this one become 4. So minus 3, so minus 3 plus 4 become 1. So this one 3 minus 1 become 2. So intersection of asymptote become 0.5. Okay, next rule number 5. We have to determine the J omega crossing. So in order to determine this J omega crossing, we can apply root always technique, because J omega crossing occurs when pole located on the J omega axis. So in order to find that one, so first we have to find the value of K maximum where the system become oscillate. So we just apply this RH table. So in order to solve this RH table, so we use the same formula that you have learned in the control fundamental in the last semester. So where first we just put the first row with the odd coefficient. So that means for the first row we just put 1 and based on this coefficient, and then 2 plus k based on this coefficient, and after 4 plus k is plus 0, so we just put this one equal to 0. Okay, for row number 2 we just put the even coefficient, so we just put this one 3, 4k and 0. Okay, for the next row, we have to solve by using formula that you have learned in the previous control fundamental. Please recall back what you have learned in the control system fundamental. So where the formula that we use is this value time with this value minus this value time with this value, and all this we divide by this value. Okay, so we apply that and then we get this equation. Okay, for this one same, we just use this value time with this value, and because this one is 0, so that means this one time this one become 0. Minus this one time this one, and also same because this one 0, so this one become 0. So 0 minus 0 becomes 0, divide by this value and divide by 3. So 0 divided by 3 become 0. So when this column is 0, so the next column become 0. We just put here 0. Okay, for the last row, this one, so we use the same formula, and this value time with this value minus this value time with this value divide by this, and then we get 4k. Okay, this column we just put 0 because previous row at the same column is also is already 0, so that means we no need to calculate for this column, we just put 0. Okay, after we complete this RH table, so we can find the value for K maximum. Okay, how? So we just take this value must be greater than 0, and from there we know that K greater than 0. And next we take this value must be equal to 0. So from here we solve, we get k less than 6. So that means from this information, so we know that k must be between 0 and 6. In order to obtain the location of pole on the J omega crossing, so we have to use this k. When k is equal to 6, so that means the location of pole are on the J omega crossing. So based on the auxiliary equation, we just take the equation for the s power of 2 here, and this one 3s square plus 4k equal to 0, and we just put this value, this maximum value 6 here, and then we get s is equal to plus minus j 2.83. Okay, next for rule number 6, we have to identify first either this system have breakaway or break-in point. So based on the location of poles, and when k is equal to 0, so we have 3 poles on the real axis. So the breakaway point only can obtain when there are more than 2 poles on the real axis. So in this case, we have three pole on the real axis. So that means we have to find this breakaway point. Okay, for break-in point, so this break-in point only occurs when there are more than two zeros on the real axis. In this case, we have only one zeros on the real axis, so that means there is no break-in point. Okay, to find the breakaway point, in order to calculate the breakaway point, first we have to find the equation for Ks. So based on this characteristic equation, so K is equal to, we just rearrange this equation. So K is equal to S cube plus 3S square plus 2S divided by S plus 4. Okay, we just ignore this negative function because we use this modulus here. Okay, so after we get this K, so in order to find the breakaway point, we have to differentiate this K with S. Please recall back what you have learned in calculus. To solve this case, so we have to employ this formula, okay, where differentiation of K over ds equal to V du over ds minus U dv over ds divided by V square equal to 0. So V is referred to this equation and U is referred to this equation. So du over ds, we just differentiate this equation like this, okay? While for V, dv over ds, we just differentiate this equation. Okay, after we get all these values, so we just put in this formula and then we just put vs plus 4 here, okay, times with du over ds and this equation we just put here minus u we just put this equation here times with dv over ds is equal to 1, just put here 1. Okay, this v square we just put on the right side, and so after we put on this side and then we time with 0, so the value become 0. So that's mean after we solve this equation, so we get s is equal to negative 5.42, negative 1.62, and negative 0.45. So that's mean we have three value of s here. So which value is considered as a breakaway point? And because in this case we have only three pole, and one pole will go to the zeros, and because we have one zeros here, and another two pole will separate, one go to the positive infinity and the other one go to the negative infinity and separate at the breakaway point. So which one of these S represent breakaway point? Based on the location of pole and zeros, so this pole is close to this zero. So when K increase, this pole will move to this 0. The other two poles, when K is increased, the two pole will meet at this point and then separate. One go to the positive infinity and the other one go to the negative infinity. So based on this, the breakaway point will occur at negative 0.45. Next, from the parameter that we have calculated, based on that 7 rules, we can draw the root locus. First, we draw the S-plane, okay, like this. So this is the real axis. And next, we draw the imaginary axis. Okay, we put the scale for this S-plane, and then we put the location of poles and next location of zeros. Based on angle of asymptote and intersection of asymptote, we can draw the line for this asymptote. So where the angle for asymptote is 90 degree and also 200, start from here to here, 270 degree, with intersection of this asymptote is at 0.5. That we put the location of j omega crossing, okay, this one. After we put all this information, so we can draw the root locus like this. And also from this root locus, we can know the performance of the system. Either the system is operate under overdam, underdam, undam, and so on. So, for example, if the location of pole move from the original location to uh, the other location, for example, to here, so that's mean the system from over them will change to under them case. So when this pole and this pole is meet at this point, at the breakaway point, so the system become critically damp case. Next, when the K is keep increase till the location of pole on this J omega axis, so the performance of the system become undamped so that the response of the system become oscillate. In the case of this pole location outside of this left hand side, the system become unstable. Let us look at this example. For the response with settling time Ts equal to 10 seconds, identify the location of poles. Second, determine the value of proportional gain K. And next, find the percentage of overshoot. So to settle this problem, first we have to know the relationship between setting times and this root locus. Through if we know the location of pole, so we can identify the value for zeta omega n and also the value for omega d. So as we know, the formula for Ts is Ts equal to 4 divided by zeta omega n. So in order to make sure the Ts is equal to 10, zeta omega n should be 0.4 because the formula for zeta for Ts is 4 divided by zeta omega n. That means when 4 divided by 0.4, so you will get the result become 10 second. In order to make sure this settling time can be achieved, so we have to make sure the location of pole should be for the real part at 0.4. If for 0.4, if we look at this root locus, the location is somewhere here. So that's mean we just take this location as a location of pole. So in this case, the location of pole is at negative 0.4 plus minus, and because this is a conjugate for the complex part. So the location of pole when the system operate for certain time 10 second is at negative 0.4 plus minus j 1.05. The value for proportional gain K can be obtained by substitute this S into this equation. In order to find the gain K, so we can use this formula K equal to 1 over modulus of GS, where S in this case is referred to coordinate location of poles when TS operate at 10 seconds. We just substitute the value of S in this equation, and then we get the result for K is equal to 1.28. Next, in order to find the percentage of overshoot, so we have to draw the line for zeta. Line for zeta should be cross the location of pole when when ts is equal to 10 second. So we just draw the line like this. So this crossing point is a location of pole when system operate at ts equal to 10 second. So in order to find zetas, we have to find the angle theta, angle from here to here. So in order to know this angle, so we can use protector. So we just put this protector here. Okay, based on this line, the measure value for this protector is at 60 degree. So that's mean this theta is equal to 60 degree. So in order to find damping ratio zeta, so we just use formula zeta equal to cos theta. So when theta is equal to 60 degree, we just put here 60 degree and then we get zeta equal to 0.5. So after we get this value of zeta, so we can calculate the percentage of overshoot where percentage of overshoot we can find based on this formula. As you can see, it's depend on the value of zeta. So we just substitute this value of zeta in this formula, and after we solve this, we get the percentage of overshoot for this system when put at this point is 16.3%. Okay, hope you can understand this example. Thank you.